Okay, so this lecture is going to be about backpropagation in CNN architecture. Before we get started with this topic, there are two things that I want to point out here. First is that since we are learning the concept of backpropagation in CNN, or since we are going through the topic of CNN, then I'm just assuming that you are already aware of the concept of backpropagation in ANNs and machine learning. So I'm assuming that you have a basic idea around how the parameter training happens in a machine learning algorithm or in an architecture like artificial neural network, and you have a decent understanding around gradient descent as well. So in case you are not comfortable around these things, then you can consider checking out the backpropagation lectures from the deep learning and machine learning playlist, and then you can come back to this particular video so that it makes more sense to you. And the second thing that I want to point out here is that this backpropagation thing in CNN is something that you will not have to be bothered about when you are working in a CNN project, or I should say when you are using a convolutional neural network architecture. Your code will handle everything over here, but it is just that being a good data scientist, you should have some clarity that what is actually happening behind the code execution. And this is why, for your general understanding and from the interview perspective as well, it is important that you should have some idea around backpropagation in CNN architecture as well. This should not look like a black box to you. Okay, so keeping these two things in the mind, let's go ahead and proceed with the topic. So if you have been following in sequence, then so far, going by the previous lectures of CNN, you should be already comfortable around convolutional layer, and you should have clarity that what are featured maps. We also discussed around pooling, different types of pooling like max pooling, min pooling, average pooling, etc. And exactly how after applying the pooling method, the featured map gets reduced in size. Then we apply another convolutional layer, and then we apply another pooling if required. You can add or remove the number of layers for convolution operation and pooling both. So there is no concrete rule around that you should have at least this number of convolutional or pooling layers. So it is completely your choice. We also understood that what is the meaning of the flatten layer, where basically what we do is we take each and every row of pixel that we have within the image, and then we stack it on top of each other in order to create the input column. This is the thing which happens in flatten layer. And then we pass this information to the fully connected layer, which is the ANN attached to the end of the CNN architecture. And by the end, you get the classes with probability values in order to do the classification of the object within the image. So within last 3 to 4 lectures, we have discussed around all these topics. We have also discussed about the concept of padding and strides as well. So if your understanding around all these things are absolutely clear, then we can go ahead and discuss about backpropagation now. So first of all, I will quickly erase all this to make it more clear. And in order to understand the backpropagation in CNN, I'm going to create a simpler version of the CNN architecture. So let's say that we have an image here, and the size of the image is 6 by 6. And then we have a filter or kernel matrix. So it is filter, or you can call it kernel. And this kernel matrix has a size of 3 by 3. So basically we are going to use this filter to convolve over the top of the image. This is something that you should be anyways comfortable with going by the previous lectures, as we have already discussed this. And after doing the convolutional operation, the next thing that you will get will be a featured map. And since the image is in a size of 6 by 6 and the filter we have in a size of 3 by 3, going by the formula that we have discussed earlier, which was m minus n multiplied by m minus n plus 1, actually m representing the size of the image, m by m, and n representing the size of the kernel matrix, which is n by n. This feature map will be in a size of 4 by 4. And since over here we are considering only one filter, this is why you can also call it in a size of 4 by 4 by 1. So let's assume that over here, instead of having only one filter, you have 2 more filters like this, okay, of the same size. In that case, over here you will have two more feature maps like this, and the size of the feature map will become 4 by 4 by 3. But anyways, since for the simplicity purpose we are considering only one filter, so we are going to have only one feature map. So I'm erasing all this. After achieving this feature map, the next thing that we will do is we will apply ReLU, which is a simple operation of converting all the negative values into 0, nothing else. So obviously this will do no change with the size of the feature map, and the size remains 4 by 4. And as you already may guess that the next step will be applying pooling operation. And after applying the pooling operation, as you know, the size of the featured map will be reduced. So it shrinks to 2 by 2. So basically we are taking this image, then we are applying the filter to do the convolutional operation in order to achieve this featured map that will have the features from this input image. Then we apply ReLU operation on top of this feature map to achieve this one, and then we apply the pooling operation to get a featured map which is reduced in size. So basically in this architecture we have only one convolutional layer and only one pooling layer. And since this featured map is reduced in size and it is in a size of 2 by 2, which means it is basically an image of extremely low resolution that has only 4 pixels. So in practical, obviously you will not work with images of this size, but again try to understand, I'm keeping this entire thing simple just to give you a better explanation, nothing else. And the next step will be to create the flatten layer. So basically what we need to do is we will take this image or the featured map, and first we will take the first row of pixel and place it like this. So this will have 2 values. Then we will take the second row of pixel and we will place it on bottom of this, and this will also have 2 values. And this entire thing becomes the input of the fully connected neural network towards the end of this CNN architecture. So I will write it as ANN. And again, please do not consider this as a single neuron. This circle at the end is representing an entire neural network. So basically, this ANN thing that I have drawn towards the end is representing this, a neural network that will have 4 neurons or perceptrons in the input layer, because we have 4 values in the input over here. Then you will have number of hidden layers, you can choose that. And finally, we will have one output layer. And this particular ANN thing is representing this whole architecture. So I try to explain you this thing so that you don't have questions in your mind that in the input layer, if we have 4 values, then how come we have only one perceptron over here? Okay, so this is actually not a perceptron. This is representing an entire artificial neural network architecture. And now I'm going to make the screen a bit more clean by erasing the unnecessary stuff. Right. So this is a very basic CNN architecture that we are considering in order to understand the backpropagation operation. So going by your previous understanding of backpropagation in ANN or in any other machine learning algorithm where you will have trainable parameters, we already know that the basic idea of backpropagation is nothing but propagating backwards in your architecture in order to adjust the value of your trainable parameters. So obviously over here we are able to understand that how the forward propagation is happening. We take the image and we take this filter or kernel matrix to do the convolutional operation that gives us this feature map. Then we apply ReLU function to discard all the negative values and replace them with zeros here. Then we apply this pooling operation in order to reduce the size of the featured map, and then we apply the flattening method in order to have the values as an input layer for the ANN architecture. And once this ANN architecture gives you an output, let's consider that as y hat. Over there, obviously we will use a loss function in order to check that how close we are in compared to the input value, the actual value. And as a loss function, you can either go with binary cross entropy in case you have only 2 classes in your target column. Let's say you are doing a classification between cat and dog, or you can also use softmax in case you have more than 2 classes. And this will be the entire idea of forward propagation starting from the image towards the end of the architecture. So as a next step, Backpropagation will happen in order to adjust the values of all the trainable parameters. And before we understand about that, let's try to understand first that how many trainable parameters we actually have within this particular architecture. So the parameters for which we need to adjust the values in order to reduce the loss are, first of all, all the values within this filter. So 3 by 3, which means 9 values that you need to adjust here. And plus this filter matrix will also have a bias value, a scalar value. Okay, so I'm taking that as well. So 9 plus 1. Additionally, let's check that where else we have trainable parameters in this architecture. So after flattening this particular matrix or featured map, when we acquire our input values, so for example, we have 4 values over here, which is being passed to the fully connected neural network or the artificial neural network architecture. Then obviously each and every value will have a dedicated weights assigned to it. So it will have W1, W2, W3 and W4. So we have 4 weights over here, plus let's also consider a bias term over here as well. So let's take it as B2 and here we will take it as B1. So we have 5 trainable parameters towards the end as well. So it will be 10 plus 5. So in total we have 15 trainable parameters for which the values needs to be adjusted in order to reduce the loss that we have. And since now we have understood that how many trainable parameters we have, let's try to understand the backward propagation operation over here. So basically I want to keep this lecture in such a way that this should be the only video that you will ever need in order to understand the backpropagation in CNN. So definitely this is going to be a bit lengthy. So please have some patience and stick to the end. So before we move ahead, what I want to do is I want to generalize this entire architecture. Okay, because over here it is looking very complex and this might seem a bit difficult if I'll try to explain you backpropagation on this particular figure. So let me place it over here on the top and let's continue from here. So let's say that you have an image X and you apply the convolutional operation on top of this. So let this be the symbol of the convolutional operation, which is happening with the help of a kernel matrix or filter that has some weights and that has a bias as well. And after doing this convolutional operation, you get a featured map and let's call that X1. What is the next step then? Obviously, you apply the ReLU operation on top of this. And let's say after applying this ReLU operation, you are getting R1. And then the next step would be applying max pooling on top of this. Although you can use any type of pooling, but for the time being, let's consider we are using max pooling. And then let's say you get P1. The feature map is now being called P1. What will be the next step then? Obviously, you will apply flattening and this will give you the input layer. Let's call that F. This F will be passed on to your artificial neural network architecture, or you can say the fully connected neural network. And let's say that will give you an equation S, which will be then passed on to an activation function like sigmoid that finally gives you the output Y hat. So let's do one thing first. Let's shrink the size of this simple architecture a bit so that it can fit well on the screen. Alright, so now this output value Y can be used in order to calculate the loss to check that how well we are doing the prediction. Now the way we have the trainable parameters over here, we also have the trainable parameters over here as well. So if you remember what we discussed on the top, that when we are passing on the input values to the fully connected neural network, here as well we have 4 parameters and 1 bias value, right? So I'm talking about that only. So let's call it as W2 and bias 2. So remember that this W1 has 9 values because it is a filter of 3 by 3 size plus 1 bias value. So in total there are 10 trainable parameters, and over here we have 4 weights plus 1 bias. So these are the parameters for which we need to adjust the values during backpropagation in order to reduce this loss value, or you can say in order to do more accurate prediction, since the better you predict, the lesser loss you will have, right? So basically we want to update the values of these parameters, right? And if you remember by the previous lectures of deep learning or machine learning, we use the formula of this gradient descent algorithm in order to update these values. So what does the formula say? Let's say we want to update the value for this parameter W1. Okay, so the new value for this weight will be equals to the old value of W1 minus a small learning rate multiplied by DL by DW old. Now what does this mean? It simply means that how the value of loss is changing by bringing a very small change with the value of W old. So obviously at this point of time I am assuming that you are anyways comfortable with the extremely basic calculus or the idea of derivatives, so I am not going to focus so much on that. And in exactly similar way, we also update the value of the bias as well, just like this. Okay, so basically we are looking for these new values. Okay, and let's see what we already have. We have the old values that we initiated randomly, okay, that we have actually used in order to do the front propagation, in order to achieve this output and to calculate the loss as well. We know the value of this learning rate because this is something that we have decided or chosen by the algorithm. So that is also within our control. All we need to find is the value for this, the derivative of loss with respect to the previous value or the old value of the weights. So the idea of backpropagation is nothing but calculating this particular thing. Okay, so I will erase these things first and let me bring this entire portion to the side over here. Okay, so the next thing that we are going to do is this entire CNN architecture. Okay, I want you to assume it in two parts. First will be this, the convolutional part, and second will be this, where we have the fully connected neural network. And within the previous lectures of this particular deep learning playlist, we have discussed a lot about artificial neural networks, and we have also discussed about how the weight adjustment or the values of the weights are being adjusted in the artificial neural network during the backpropagation. So anyways, you will have a decent clarity around that if you are following along with this playlist. The challenging part over here to understand is that how the backpropagation happens in the flattening layer, in the pooling layer, also for the ReLU operation, and most importantly within the convolutional layer, how exactly it is happening over here. So obviously this part is going to be the crux of this lecture, but still I will quickly go ahead and cover very quick how the weight adjustment is happening here. So I'm talking about these weights actually. Okay, so basically what we want to understand that how the loss will be changed with respect to a change with W2. Okay, or over here you can also say B2, but let's consider W2 for the time being and try to understand that W2 or the weights for the W2 parameter is not directly involved in order to calculate the loss, because using the values of W2 or B2 or this entire weights, these 5 weights, first we are calculating this equation S, which is then being passed on to the sigmoid function in order to calculate the output, which is Y. Using the value of Y, we are then calculating the loss. So now we will have to propagate backwards in order to understand that how we calculate DL by dW2. So let's try to understand that. So obviously this is the point where we are going to talk about chain rule. So what does the idea of chain rule say over here? First we will check that how the value of loss will change by bringing a small change in the value of Y hat. So that will be DL by dy hat. Next step will be how the value of dy hat is being changed by bringing a change in S. So that will be dy hat by ds. And then finally we will calculate that how the value in S will be changed by changing the values of W2 or B2, let's say. Anyways, both will be calculated in the same way, but for the explanation purpose I am considering W2 for the time being. So this will be ds by dW2, and applying the method of chain rule, this will cancel this and this will cancel out this, and this is how we calculate dl by dW2. And by finding this particular derivative, what we basically try to check is that what happens when we are moving or changing the value of W2 in a certain direction. So let's say if we are increasing the value of W2, and that is leading to the increasing value of loss as well. Then obviously the gradient descent formula will not update the value of W2 by increasing it. Instead, it will go for the other approach by trying to decrease the value of W2, and it will check if the value of loss is decreasing in that way. This is how the weight updation works. Anyways, this is something that we have already learned in a lot of details when we were discussing backpropagation in ANN. But still, I thought of giving you this much explanation for a revision purpose maybe, so that you should be feeling comfortable within this lecture. So hopefully, we are clear about the weight updation part for this ANN part of the CNN architecture. And we are able to understand that how these weights are being updated or adjusted by doing the backpropagation, by calculating different derivatives and applying chain rule in order to achieve the optimum weights for these parameters. And now we are going to understand step by step the idea of backpropagation within the convolutional part of the CNN architecture. Since we are propagating backwards from the end, and we have understood how we are calculating or updating these values, which means we have already understood that how to calculate this particular term, right? Now let's talk about the updation of these weights. So again, for the explanation purpose, I am considering only W1 to show you how the weight updation happens, and the same method or the same trick will be applied for B1 as well. Okay, so basically we want to understand that how the loss is being changed with respect to W1. Okay, so obviously coming back from the point of loss, we are already here at this point where we have calculated or we have understood how dl by dw2 is being calculated. Now let's try to flow backwards from this point. Okay, so we will further apply the chain rule, and we need to calculate the derivative of w2 with respect to, so from this point we will now capture this one, so p1. Next step will be to calculate the derivative of p1 with respect to the derivative of r1, so this one multiplied by, let me erase this one. Okay, we will calculate the derivative of r1 with respect to dx1, and then finally dx1 by dw1. Again, going by the chain rule, this will cancel out this will cancel out this, and so on. And we will finally end up calculating that how loss is changing with respect to bringing a small change in W1, which is this weights, W1 or B1 you can say, because obviously you can understand the way we are trying to update the value of W1 using this chain rule method, the value for B1 as well will be updated in the similar way. So let me make it cleaner again. Since this part is all clear for us, we understand very well that how the weight updation happens for the ANN architecture. Let's talk about this part. So how do we calculate the derivative for the flattening layer? So let's understand about backpropagation in flattened layer. So previously, if you will check what we were doing exactly in the flattening layer, after applying the pooling operation, the size of the featured map will be reduced from 4x4 to 2x2. And basically we were taking this 2x2 matrix and we were flattening it in order to have the input column or the input values. And during backpropagation, we need to understand that how do we go back from this step to this step, right? So let's understand that. So after applying the pooling operation, we had this matrix of size 2x2 that we were calling as P, or let me erase it from here and write it here, P. And then what we were basically doing is we were applying the flattening method in order to create this array that will have 4 values to pass it on as an input to the fully connected neural network. And when doing backpropagation, we do the exactly opposite of this. We take this input column, okay, these 4 values, which was previously in a size of 4x1, that means 4 rows and 1 column, and we restore it back to the previous shape of 2x2 like this. That's it. That's all happens when we are doing backpropagation in flattening layer. So let's go to the previous explanation. So previously we knew that how we calculate this P1 by applying max pooling, and we flatten it in order to have the input value. But during backpropagation, we restore the input values back to the previous shape of 2x2 or whatever the shape was previously. So this is what happens in the step of dW2 by dP1. Okay, now let's move further in the discussion of backpropagation. So starting from the loss, we came here to here, we updated the weights, and we also understood that how backpropagation happens in the flattening layer. Now it is time that we understand that how backpropagation is happening in the pooling layer. So let's discuss over that now. So just like the flattened layer, again we do not have any trainable parameters here. So we are not gonna using any conventional backpropagation. Instead, we will again do exactly opposite of what we have done previously during pooling or max pooling operation. So if you remember the max pooling operation in this way, let's say if you have a structure like this, okay, let me draw it completely, then I will explain. So let's say that you have an image like this that has a size of 4 by 4 and in total it has 16 pixels. Then when you are applying max pooling, basically what you're doing is you take a window of 2 by 2. Okay, this could be of any size, but let's say 2 by 2, and you start moving this window on top of the image, and for each and every position, let's say initially the window is over here, then specifically when you are applying max pooling, you take the maximum value out. Okay, so from the first position you will take 4, again you move the pooling window to the left and you take out 8. Similarly, you place it over here this time and you take out 12, and finally in the last position you will be taking out the highest value, which is 16. Okay, this is more or less the entire idea of max pooling. But when you are doing backpropagation on the pooling layer, you do exactly the opposite of this particular operation. So let me tell you what exactly happens here. You take this matrix, okay, and then you move it backwards to the previous shape. And it is really important that while doing this backpropagation, we should have a note that from which particular index we have taken the maximum value, like these ones, okay? Because when we are restoring the information backwards in the previous shape, only that particular position from where the maximum element has been taken out, only that position will be non-zero, and rest of the part we will keep it as 0. But let me tell you one thing again, that none of these things will be done by you manually. Okay, we have already discussed this particular thing at the beginning of this lecture, that the entire operation of backpropagation will be handled by your code only. It is just that you should have some understanding that what is actually happening behind the code execution, so that a typical CNN architecture should not look like a black box to you. It is really important from the interview perspective. And this is how the backpropagation happens in the pooling layer. Obviously, there are no trainable parameters. All we are doing is we are doing the reverse of the previous operation. So initially it was a 4 by 4 matrix, and by applying the max pooling operation, it got converted to a 2 by 2 matrix. During the backpropagation, we take this 2 by 2 matrix and we store it back to the previous shape in this way, keeping the positions from where the highest elements were taken as non-zero. That's it. And with that being said, we have now also understood that how this particular part is being calculated. So now we need to understand the next step, where we will understand how the ReLU operation is being considered during backpropagation. So this one is going to be the most simplest thing to understand. Okay, see what is happening within this ReLU operation. All we are doing is, let's assume over here we have a 2 by 2 matrix. Okay, something that looks like this. Let's say 2, -3, -1 and 6. Then all we are doing is, after applying ReLU on this particular matrix, there will be no change in the shape of this matrix. It is just that all the positive values will remain same and the negative values will be converted to 0. That's the basic thing that ReLU operation is doing for you. This is first thing. Secondly, in order to calculate this DL by dW1, which means in order to understand how the loss is changing with respect to bringing a small change in W1 or B1 for say, we calculated, or we are trying to apply this particular chain rule, right? And we have understood that how the calculation is happening till this point so far. Okay, so when you are propagating back from the point of loss to the point of ReLU, which means from this particular point to this particular point, After propagating back towards over here, the output that you will have, that also is going to be a 2 by 2 matrix. And let's say this particular 2 by 2 matrix looks like this. Let's say 1, 3, -6 and 2. Okay, so basically over here what you are trying to do is you are trying to calculate dr1 by dx1, which means the derivative of these values, all the values within this particular matrix, right? So you will try to calculate d1 with respect to dw1 because we are checking for w1, right? And similarly you will try to calculate the derivative for other elements as well. So the idea is going to be very simple. If you are doing the derivative for a positive value like this, this or this, you will always get 1. Obviously you know that going by the basics of calculus. Otherwise you will get 0. That's it. That's the whole idea behind it. Okay, so if anyone asks you in an interview that during backpropagation in a CNN architecture, how does the backpropagation happens in the ReLU layer, then you simply say that within this particular step, exactly here where we are calculating dr by dx1, we are trying to differentiate the values of r1, right? R1 is nothing but a 2 by 2 matrix that has 4 values, and we are trying to calculate the derivative of those 4 values only. And for those 4 values, if the values are positive, then obviously the derivative will be 1. Otherwise, the derivative will be 0. That's it. And finally, since we are done till this point in the backpropagation journey, now the last step is to calculate this dx1 by dw1. So basically for this particular filter, okay, where we are using a 3 by 3 filter over here. So let's say for simplicity purpose that we are using a filter of 2 by 2. Okay, that looks, let's say something like this, something like 0, 0, 1 and 1. Okay, so now during backpropagation, we will try to update the values of this particular filter into any random number. Okay, although that will not be random, the values will be updated in such a way that the loss should be minimum. But the idea is to have the values in such a way that these values within the filter, when applied on the image during the convolutional operation, this should derive some meaningful features. That's it. So I'll try to explain what I mean here. Let's consider a very simple use case. Let's say that you have an image. Okay, in the image you have a round object like this. Okay, and then you have a 2 by 2 filter that you are using, size 2 by 2. Let me write it outside. Okay, 2 by 2, and this will have random values like x1, let's say x2, x3, or let's say x4. Then what's the idea of using this particular filter? We will convolve the filter on top of the image, first at this position, next over here, stride by stride, then over here, then over here, right? So after convolving the filter all over the image, we should be able to grab some meaningful features or edges, right? Like some primitive features like this, this, and then towards the end of the convolutional layer, finally we will be able to identify the object like this. Okay, but let's say the values of your filter are kept randomly in such a way that it will detect horizontal edges like this, or let's say vertical edges like this, or let's say slant edges like this. Then you only can think that combining this kind of edges, you will never be able to form a circle that you have on the image. So when you finally float towards the end of the CNN architecture over here, the loss will be too much. When you calculate the loss using binary cross entropy, or let's say softmax, the loss will be very high. Okay, because the edges that you are trying to capture with the help of this particular filter, those edges are not really that meaningful in order to identify the object within the image. So the backpropagation happens exactly the way we have learned. This backpropagation happens, and we adjust these values in such a way that this time we will try to capture another type of edges. Maybe edges that instead of being horizontal or vertical edges that may look like this, curved edges like this, primitive edges, okay, like this. In that case, combining edges like this, and obviously let's say if we are talking about detecting 4 edges, okay, first like this, second this, third this, and fourth being like this, okay, in that case you will need to have 4 filters. So you will have 2 by 2 size 4 filters, and you will apply them one by one for the convolutional operation on top of your image. And by doing the backpropagation again and again, the algorithm finally succeeds to update these values in such a way that they will start capturing edges like this. Okay, this is the whole idea of doing the backpropagation in CNN. Finally, you will have these values. Let me make it a bit cleaner. This is looking very untidy. So in a CNN model, when you're doing the backpropagation in order to reduce this loss, okay, and we discussed all of this. How do we calculate this step, then how do we backpropagate on top of flattening layer, max pooling layer, ReLU layer, and finally after coming to this point, the algorithm will start updating these weights and biases the way it was updating these weights and biases. Okay, finally in the end, when we have achieved the best values for these weights and biases, which is nothing but the best values for the filter that we are using. Okay, if we are able to do that, in fact we will not be doing that, the algorithm will do that for us, but finally we reach to the point where we get the best values for the filter, and then the filter will start capturing the meaningful edges or features from the image. And then finally, if you pass an image of a Tweety bird, then since these filters have the best values in order to capture the edges or features like the eyes of Tweety bird or its eyebrows or head or other features, it will pass the information towards the end of the architecture so that it can confidently say that it is an image of a Tweety bird, not of Goofy or Donald Duck. So I hope this lecture was able to provide you some understanding, a very decent understanding around backpropagation in CNN. In case you are learning this topic for entirely first time, if CNN is completely new to you, in that case you may require to go through this particular video maybe a couple of more times, but please do not hesitate doing that, because initially I also struggled a lot to understand this particular topic. And congratulations if you have already understood it. Try to share it with your friends or peers who may find it useful. And thank you very much for watching till the end. We have learned a lot within this deep learning playlist. Although it is becoming very difficult to make time from my full-time job to create tutorials like this, but I will try my best to create more tutorials on recurrent neural network in order to continue this deep learning playlist. So please subscribe to the channel if you're new here, and hopefully I will see you in the next lecture.